So this is the outline of this lecture. First of all, we'll see the basics of the p-n junction. We will see what happens if p and n-type material are brought together. Then we will see the diffusion and the drift current that is present in a p-n junction, and we will see the barrier potential as well. And we will derive the expression of the barrier potential, which is a very important parameter in a p-n junction or in a diode. And then we will find out the width of the depletion region of the p-n junction. And finally, we will see the p-n junction in forward and reverse bias conditions, which is the basis of the diode. So this is my p-type material, and this is my n-type material. And we know that in p-type material, the majority charge carrier are the holes. We also know that it has minority charge carriers as electrons. We will see that part a little later. And in n-type, the majority charge carriers are the electrons. So now, when these two types of semiconductors are brought together, these holes will get diffused to this n side, and the electrons will get diffused to the p side. This diffusion will happen because of the difference in the concentration, because you can see here, even though there may be holes due to the minority charge carrier, but they are very less, okay? And here it may be electrons, but as a minority charge carrier in the p side, but they are very less. So because of which the hole will get diffused to this n side, and the electrons will get diffused to the p side. So let's see what happens because of this diffusion. So when the electrons leave this n side and comes here, so it will occupy this hole and it will become negatively charged here. This is because the p-type material is a neutral substance by itself. So when the electrons comes here, it will become negatively charged. So if you see here, in case of the p-type, if you remember, we need one electrons here, right? Because there is a missing electrons, there is a hole. So if electron comes from the n side and occupy this space, that means, so there will be imbalance in the charge and it will be a negatively charged substance. Similarly, on the n side, if the electrons goes away from this, if the free electrons goes away, the positive charge of the nucleus will be uncovered. So basically there will be an imbalance in the charge. So in this n side, it will be positive charge, because as we know that the positive charge of the nucleus will be uncovered when the electrons goes from the n side to the p side. So we can say that either the holes has diffused from the p side to the n side and gone here, or we can say that the electrons has diffused from this n side to the p side. And the overall result will be that this charge region is created and both of the charge regions are equal, because the overall, if you see the p and n type material, it is still again a neutral substance. So this region is called the depletion region, okay? This is called so because they are depleted by the charge carrier. There are no more charge carriers in this region. Now one may ask, okay, there is a diffusion, but how long will the diffusion happen? So because of this charged region, there will be an electric field, okay? There will be an electric field E that is created from this positive charge to this negative charge. And this electric field will stop the further diffusion of the holes from the p side to the n side, and the electrons from the n side to the p side, because we know that the holes move in the direction of the electric field and electrons move in the opposite direction of the electric field. So this is called a barrier. So it will create a barrier potential, something like this. So this barrier potential will prevent the further diffusion. However, this barrier is not a perfect barrier. There will be a leakage in the sense that there will still be a diffusion. It is something like if you have a glass of water and it's a full of water, glass full of water, and we are using our hand to cover it. Okay, we are using our hand, and if we turn it upside down, our hand is a barrier, but still we can see that there may be some leakage of water right through our holes. So similarly is the situation here. There's an electric field which is preventing the further diffusion, but still there will be a diffusion current ID. So there is a diffusion current ID of the holes from here to here, and similarly for the electrons from here to here. And of course the resultant current of this diffusion in both the case is same, because if the electrons is moving from this direction to this direction, the direction of the current is in this direction. Similarly, if the holes are moving from this direction to this direction, the direction of the current is also in this direction. So initially the diffusion current was huge. This ID is huge, right? When the diffusion started. But after the creation of this barrier potential, this has become very small. So this has become very small, or the ID is very small. But the question is, if there's a diffusion current, all the holes will eventually get diffused to this direction and the electrons will get diffused to this direction, and the depletion layer should increase. Okay. So the question is, will it happen in that way? So it doesn't happen in that way. So basically one more phenomenon is happening here. You see, we have this electric field and we have this minority charge carrier. Here in this N type, the minority charge carrier are the holes, and in the P type, they are electrons. Okay, and if you see, the direction of this electric field is favoring the movement of this minority charge carrier from N to P. Similarly, the direction of the electric field is also favoring the movement of this negative charge or the electrons from this P to N. So this will lead to a small current which is based on the minority charge carrier and which is called as IS. Okay, so if you see here, if the holes are moving from this direction, then the current direction is like this. Similarly, if the electrons are moving from P to N, then again the current direction is also like this, because we know that the direction of the current is opposite to the direction of the movement of the electrons. So both of them will lead to resultant current IS. Okay, and in equilibrium condition, this ID will be equal to IS, or in other words, the diffusion current will be perfectly balanced by the IS current, which is based on the minority charge carriers. So in equilibrium, the diffusion current ID is equal to IS. So let's note down the points, important points that we have discussed just now. So carriers are depleted from the depletion region, both on the P side and the N side as well. So an electric field E is created, and that prevents the further diffusion of the holes and the electrons on either side. Also, it results in a barrier potential V0, which decreases ID to a great extent, but it doesn't make it zero, of course. And ID is dependent on V0. So the ID is very much dependent on V0. So higher the value of V0, smaller is the value of ID. Okay. Okay, the minority charge carriers on both sides will result in a drift current. The minority charge carrier from the N side, which is the holes, is drifted by this electric field to the P side, and the electrons, which are the minority charge carrier on the P side, will be drifted to the N side, and these two currents will result in a current IS, because both of them are in the same direction. However, note that this IS current is not dependent on the electric field. It is dependent only on the number of these minority charge carrier, because we know that as soon as this minority charge carrier, this plus comes here, it will just get drifted. Okay, so the number of the charge carrier, minority charge carrier, which are crossing this border, which basically will lead to the current, right, is, is dependent only on how many minority charge carrier are present. It doesn't depend on the electric field, because as soon as it comes here, it just swept away. Okay, so whether the electric field is high or low doesn't matter, it goes to the other side as soon as it comes here. So however, it is not dependent on the P naught or the electric field, it is just dependent on the temperature. So it is dependent on the temperature, because we know that the minority charge carrier or the concentration of the minority charge carrier is dependent on the temperature. So higher the temperature, more covalent bonds will break and more number of minority charge carrier will be generated, and it will lead to increase in this current is. Okay, so more number of this minority charge carrier will come and it will increase this current is because of the increase in temperature. Similarly, the more number of electrons will come near this region and they will get drifted to the other side. So there is a balance of the diffusion current and the drift current in the equilibrium condition. Now suppose if there is a disturbance in the equilibrium condition because of the increase in temperature. Okay, so as I was mentioning that, with increase the temperature, this minority charge carrier is going to increase, and this will lead to increase in the is current. Okay, but now this equilibrium is disturbed. So to again balance this equilibrium, the id will also increase. Okay, the id will also increase, and what will happen is this will increase by the reduction in the v0. Okay, so the v0 will become smaller and the id will increase, and it will perfectly balance this is. On the other hand, if the temperature reduces and if this minority charge carrier decreases, if is decreases, then the id will also decrease and this v0 will increase. Okay, so the v0 will increase. Okay, yeah, so this will happen. Okay, and this balance will always be maintained. So if is increases, then id also will increase, and this will happen by the reduction in the v0. I'm describing this by the notation. Okay, and similarly, if is decreases, the id also will decrease to maintain the balance, and this will happen by increase in the v0. Okay, so lastly in this discussion, the drift current due to the holes, right, which is this is. So drift current due to the holes is perfectly balanced by the diffusion current due to the, again, the holes. Okay, and drift current due to the electrons is perfectly balanced by the diffusion current due to the electron. So this is the conclusion of this discussion. So now let's try to derive the expression of this barrier potential V0, because this is very important for the PN junction, especially when we'll use this phenomenon for the diodes and other application. Okay, so this is my PN junction, and we know that there is an electric field E in this direction. Okay, so, and if you see the majority charge carrier for these holes, we know that it is given by simply by the doping of the acceptor atoms. And the minority charge carrier, we know that it is basically, or which is basically the holes on the p side. Okay, and the electrons on the p side is Ni squared by Na. This is what we have learned till now. And similarly on the n side, the majority charge carrier, which are the electrons on the n side, is equal to Nd donor atoms, and the minority charge carrier holes on the n side is given by Ni squared by Nd. Okay, so let's draw an axis here. So maybe the border is 0, and the depletion width on the n side, let's call it as xn, and this one let's call it as minus xp. Okay, so this is my 0 of this x-axis, and this is xn, and this is minus xp. Okay, so as we have discussed, that the diffusion of these holes from this to this, resulting in a current in this direction, is equal to the drift current of these holes by the electric field. So I drift due to the holes is equal to I diffusion, again due to the holes. Okay, and we know that the expression for the drift current is basically the q mu p into, of course the e is in this direction, opposite to the direction of the x, so minus e basically, and is equal to, and we know for the diffusion current the equation is q dp, the diffusion constant of the holes, dp by dx. Okay, so yeah, so here the p is the concentration of the holes, okay, and dp is the diffusion constant, and again dp by dx is the variation in the concentration of the holes as we are going from this point to this point. Okay, so now since we know that for electric field is given by minus dv by dx, so since the electric field is given by minus dv by dx, so if I substitute here, what I'll get here is the negative will get cancelled, and of course this q and q also are getting cancelled here. So what I will get is mu p dv by dx is equal to minus dp by dx. Again dx gets cancelled here, implies my dv will be equal to minus dp by mu p. Okay, and I can bring this p this side, dp by, so now we can integrate it. Okay, so this will be integrated from minus xp to xn, so I'm integrating from minus xp to xn. Okay, and similarly I'll be integrating this one from this point to this point, where the concentration of the holes at this point is basically this one. Okay, so pp, and the concentration of the holes on this side, we know that it is pn, pp to pn. Okay, and if you remember, this is nothing but the Einstein constant, dp by mu p, okay, which is kt by q. So implies the potential at x equal to n minus the potential at x equal to minus xp is equal to, so we know that the integration of this term is ln. Okay, and this is kt by q, so minus kt by q, and this is ln p. Okay, so if I just rearrange it, what I'll get is, and of course this difference is nothing but the V0 that we are trying to find out, the barrier potential. The potential difference from here to here is V0, it's equal to minus kt by q ln if I take the negative term inside, this will be reversed. And we know that Pp is the Na and Pn is Ni squared by Nd. From here, right? Pn is Ni squared by Nd and Pp is Na. So if I substitute this value, I'll get, therefore my V0 is equal to Kt by Q Ln. So this is how I can derive the barrier potential of a PN junction, where my Na is the Na is the doping concentration of the P side, and Nd is the doping concentration of the N side. So if you see here, the V0 is dependent on the temperature as well as the doping concentration of the N and the P side. So for silicon at 300-degree temperature, V0 varies from 0.6 volt to 0.9 volt. So okay, now let's see more in details what happens to this Xn and Xp with different doping concentration. And also we'll see the width, total width of this depletion layer more in details. So consider the doping concentration of the P side, which is basically the Na, is greater than the doping concentration of the N side, which is Nd. I'm trying to graphically represent these two difference in the doping concentration. Of course, this is P side and this N side. So what will happen is the depletion region in the P side is going to become smaller compared to the N side. The reason is quite obvious because the amount of electrons present here is much sparse compared to this, so it needs to cover a longer length to balance the same amount of charge that is created in the P side. So that's why this Xn is going to become longer than this Xp or minus Xp, or this length is the absolute value of this length is, we know that it is Xp. So this Xp is going to become much smaller than this Xn. Let's try to graphically represent this aspect. This is my y-axis, which will be representing the carrier concentration. So this is my minus Xp and this is Xn. This is 0. So this is the carrier concentration of the majority charge carrier holes, which is Pp equal to Na, the holes on the P side, and of course the electrons on the P side, which is the minority charge carrier, and on the P side is equal to Ni square by Na. So basically these are the electrons, the minority charge carriers, and we have some minority charge carrier in the N side. So again, since the doping concentration of this side is smaller, so the electrons, the majority charge carrier on the N side is equal to Nd, and this Nd is smaller to Na, and observe that the minority charge carrier will be more in this N side because we know that the minority charge carrier, the holes on the N side, will be equal to Ni square by Nd. Okay, so this because the electrons are coming from here and combining with these atoms, and of course and it's getting negatively charged here, so the charge density here will be same as these Na. So this is a very important point. And similarly, these charge of the nucleus are getting uncovered, right? So as I was mentioning, in the N type, this positive charge is from this one, right? They are getting uncovered by when these electrons go away from here to the P side, right? So the density is going to be same as the density of these donor atoms. Similarly, on the P side, the electrons are coming and combining here, and it is forming the negative charge. So the concentration of the acceptor atom is going to be same as the charge density. So let me draw another graph representing the charge density. Again, this is the charge density, the X, and again, here I have my xn, and this is my minus xp. Okay, so if this is the charge density, which is same as the nd, okay, and this is the charge density which is much higher, and this is basically the, of course this is negatively charged, minus Na. Okay, so in perfect equilibrium condition, these two charge quantity are going to become the same. So the area under this and multiplied by the the cross section will give the total charge in this region, and similarly vice versa is true for this region as well. This area will give basically the q plus, which is equal to the area of the cross section. A is basically the area of the cross section of this bar, this p-n junction bar, and the q is the charge of the electrons or the holes, the magnitude of the charge, plus into this nd into xn, right? So this will give the positive charge that is there in this region, and similarly the negative charge, okay, q minus, will be given by aq na into xp. Okay, so this is the magnitude. Okay, so now in equilibrium condition, okay, these two both charges should be same, right? Because ultimately the overall substance is neutral and only the charge has transferred from one side to the other side. Okay, so or in one sense the holes has gone from this side to this side and the electrons has gone from this side to this side. So basically q minus should be equal to q plus, implies aq na xp should be equal to aq nd xn. So if I find the ratio of the xn and xp, what I'll get here is, so xn by xp should be equal to Na by Nd. So what I meant is the depletion region, the distance of the depletion region on the N side and P side, the ratio is inversely proportional to its doping concentration, which is true even from based on the simple intuition that we have seen, that if I have a higher doping concentration this side compared to this, then this xn is going to become larger and this xp is going to become smaller. Okay, so what we have seen here is that the ratio of this xn and xp will be inversely proportional to its doping concentration. Okay, so now the question is, what is this total width? Okay, what is this total width w, which is xn plus xp? So the xn plus xp can be given by, okay, so V0 is the barrier potential, Na and Nd are the doping concentration of the two sides, and this epsilon s is the electrical permittivity of the silicon. So again, this derivation we are not going to cover in this course. This is from the semiconductor physics. So where ES is the electrical permittivity of the silicon, and it is around 11.7 epsilon naught. And of course, we can manipulate these two expression and write as xn equal to okay. So you can just rearrange this equation and then get this xn and xp. So this is how we can find out the absolute, depletion region or the length of the depletion region on each side, xn and xp. Okay, so till now we have discussed a PN junction in the equilibrium condition when no external voltage is applied across it. So let's try to understand a PN junction with an applied voltage. So this is my PN junction with no voltage applied across it. So let's apply a voltage. So let's first apply a voltage which is in direction to the electric field. So I have my electric field here that is created because of this charged region. So let's apply a potential difference which is in favor of this electric field. A potential VR is applied which is in favor of this electric field, and because of which the electric field is going to increase, and this depletion charge region is going to become wider. Okay, so it's going to become larger. So more number of charges is going to come in this depletion region, and if you see the xn and the minus xp, they are going to become, this w is going to become larger compared to the equilibrium condition. And if you see the barrier potential, so basically the barrier potential was something like this initially when in the equilibrium condition. It was B0 initially. Now this is going to increase and it is going to become V0 plus VR in case of this when this BR is applied in favor of the direction of the electric field. This is called the reverse bias condition. Okay, so now because of this, because my barrier has increased, okay, so what will happen is my ID will become very small because my barrier has increased. In one sense, the ID will become almost zero if this VR is quite large enough. Whereas my IS, if you see the IS, right? So we know that in equilibrium condition, the IS and the ID was perfectly balanced. This is my ID and this is my IS. So in equilibrium condition, ID was perfectly balanced to IS as discussed before. So now what is going to happen is, since the IS is not dependent on the electric field, it is just dependent on the minority charge carrier concentration, which is dependent on the temperature. So this IS is not going to change. However, this ID is going to become zero because it is directly dependent on the electric field. So because of this application of this voltage or in the which is in favor of this electric field, so this my ID will become zero. So the overall current is going to become only due to this IS and it will be in this direction. Okay, so ID is almost equal to zero. So the current in this condition is IS, and it is also called reverse saturation current, and it is dependent on the temperature because we know that this IS is dependent on the minority charge carrier, which is dependent on the temperature. Okay, so now let's try to apply this potential opposite to what we have done here. Okay, so I have applied a potential difference VF, okay, and it is in opposite to the direction of the electric field that was created in the equilibrium region. So because of which this E is going to reduce and this the depletion width is also going to reduce. So my E is going to become very small now, and as a result of which this my ID is going to increase. So my ID is going to become very large, and of course the IS is going to remain constant because it is not dependent on the E. And if you see the barrier potential, it is also going to get reduced. So the barrier potential will going to get reduced to V0 minus Vf. Okay, so it is going to reduce by Vf. This condition is called forward bias condition. And in this case, the overall current is going to become in this direction, I. So the I is going to become this ID minus IS. But over a period of time, as we increase this BF, this ID is going to become much larger than IS. So it is will be almost equal to ID only, because this ID is going to become much higher than IS. Okay, so if you see here, basically what happens is, we will see later in the next discussion, the next lecture, we'll see how do we derive this ID and what's the expression of this IS. Note that this current IS is of the order, 10 power minus 12 ampere, or it can be lesser, and with a suitable increase in this BF, this ID can easily go to milliampere range. Okay, so this is like a picoampere and this is like a milliampere. So in this forward bias condition, a large amount of current is going to flow. It is like a short circuit. It's going to behave like a short circuit. We will discuss this one more in details. Whereas in reverse bias condition, because this IS is very small in picoampere, so this is as if like it's a off condition. Okay, it's like an off. Okay, even if this current IS is there, but it's going to become like an off condition. Okay, so this is how a PN junction can be used as a diode, right? In forward bias condition, it is conducting current, whereas in the reverse bias condition, it is not conducting current. So before we end this discussion, let's us try to find out the width of this depletion region in all the three conditions, in the equilibrium, reverse bias condition, and the forward bias condition. In equilibrium, W is Xn plus Xp is given by 2 epsilon Sq 1 by Na plus 1 by Nd into V0. In reverse bias condition, W equal to Xn plus Xp is given by, we just need to add the Vr here. V0 plus Vr, okay? And in forward bias condition, Xn plus Xp will be given by Okay, so we just need to change this built-in potential. So once we change this built-in potential function with plus Br or minus Vf, we will get the width of the depletion region either in the reverse bias condition or in the forward bias condition. In the next lecture, we'll try to derive this current ID as well as we will see the expression of this IS. Okay.